Hello, everybody. I'm very excited to introduce our next invited speaker, Arie Gurfinkel. Arie is an associate professor in the Department of Electrical and Computer Engineering at the University of Waterloo. Prior to that, he had several research positions at CAV University, at the Software Engineering Institute, and at the Computer Science Department. His main interest includes automated reasoning, abstract interpretation, and structural model techniques. He is a lead developer of many verification tools, such as Spacer and Seahorn. And today we're going to talk about problem verification with constrained processes. So,
Thank you. I want to thank the CAV chairs for inviting me. And I want to say that it's very inspiring to speak right after the morning sessions about SMT, because really the thesis of my talk today is that we can and we should make model checking be SMT. So really the thesis is that software model checking or model checking or analysis of push-down systems is basically reducible to satisfiability of constrained form clauses. And so we can reduce model checking to satisfiability. And we cannot just use SMT solvers to help model checking, but we can make model checking the problems of SMT solvers. And that we should do. And there's a lot of benefits in it. So we first start with what are constrained horn clauses. So as a definition, they're quite simple. There's a lot of symbols in here. I'll do some examples if you haven't seen them before. But the key point to understand here, it's a fragment of first order logic. It's not any different. It doesn't have any different semantics. It's not anything special. Just a fragment of first order logic where every sentence that we write has, see if this works. Maybe you just can't see it. Anyways, every sentence has this form where we have some kind of side condition. This is our constraint, and in this context, think of the constraint as anything that you can write in SMT, followed by an applications of uninterpreted predicates, and then imply another uninterpreted predicate. So this is sort of a rule that says if P1 to Pn become true and some side condition is true, then H becomes true. Now, as I said, in terms of satisfiability, the notion of models, everything is really just first order logic. So there's nothing special in here. And the only special thing on the slide is that because we're interested in satisfying the things, we need to somehow describe models for those things. So we have to have a way to write the model down. So we're actually going to be looking at a somewhat restricted versions of the problem where we not just care whether something is satisfiable, but whether something has a solution, that is, the model can be described in some theory. Again, usually, at least just for understanding, it's easy to pretend every time I say theory, think linear arithmetic. So we have clauses whose constraints are in linear arithmetic, and we want to get a model for them that we can describe in linear arithmetic. And I promised an example. So this is sort of the simplest system of constrained horn clauses. It represents a counter that counts up to 5. You have 3 clauses in here. One uninterpreted predicate P. The first clause is called the fact. It basically says P has all values which are less than or equal than 0. This last one, it's called the query. It tests whether P has anything where X is greater or equal than 10. So essentially, that's an assertion requiring that everything in P is less than or equal than 10. And then we have an inductive definition or recursive definition of P that if something is already in P and X is less than 5, then if we add 1 to X, then this is also in P. That's it. So if I'll ask you whether this is satisfiable or not, well, you can think for a little bit. And again, you just think in terms of first order. We're trying to come up with an extension of the underlying, in this case, theory of arithmetic with an interpretation of a predicate P to make this, to make every sentence true, every sentence valid. So in this case, if I plug, for example, for P, I'm going to interpret it as a set of all numbers less than or equal than 5. You plug it in, you see it works. And if I want to talk about solutions, I'll say, well, this system also has a solution, namely x less than or equal than 5, because this is how I can describe that set using arithmetic. And so this is just to drive this point more. So we have the original system at the top, and at the bottom we have the solution, x less than or equal than 5. And in this case, we can actually validate the solution. The solution validation is a decidable problem to do. Doesn't always have to be this way, where we just plug in, instead of p, I plugged x less than or equal than 5 everywhere. And I claim that every clause now is a tautology, and therefore x less than or equal than 5 is the solution to the system. So the foreign clauses above are satisfiable. If, like me, you think about everything in terms of program analysis, what we're doing is we have a representation of a program. This program has P, which represents the set of its reachable states. And we've just proven that x less than or equal 5 is an inductive over approximation of its reachable states. It's something that includes all of the initial states. It's something that's closed under induction. And in this case, it happens to be something that proves our property. Now, things are not always satisfiable. We have systems that are unsatisfiable. So here is a similar example. I switched P to Q, but there's really, like, the name P or Q doesn't really matter, just to make it different. It's the same counter, but the property is now different. Now I'm saying that the counter never gets to 2, and of course it can. And in this case, sort of the counter example to satisfiability is going to be a resolution proof. And again, this is nothing all that scary. It's kind of the usual resolution proof. I don't really know how to typeset resolution proof. This is kind of tricky to read, but if you really focus on trying to read it, all that's happening here, we have rules like this, which basically instantiate the universal quantifier. So here I plugged 0 instead of x, just because I decided that would be a good thing to do. And then I simplified the resulting, so 0 less than 0 is true, and I simplified this into Q0. And then here I picked a different clause, which corresponds to one step. And then I instantiate it with 0 for x again. And then I resolve this 0 against this 0, and I get a 1. So if you kind of look on the diagonal here, you'll see that we're getting a counter example. A counter goes 0, 1, 2. And now it gets to false, and the property is false. So that's it. That's what constrained foreign clauses are. This is how they're related to verification. And if you look again at what is the problem that we're solving, sometimes it may appear that maybe this is second order, but this is really just first order satisfiability, where we're saying we have this Q in the signature, and a model that we construct has to provide an interpretation for this thing. And so we're just looking for that interpretation. So as I was preparing for this talk, I started looking sort of at the history of foreign clauses, at least in my work. And I came up with this brief history of modern history of constrained foreign clauses, because of course, the notion of foreign clauses is much older than 2012. It's been used in program analysis in lots of different ways. And this is really sort of my personal history. It's neither complete nor exhaustive. I'm sure I'm missing lots of things. This is really sort of what turned me into this. And what I think influenced a lot of the current work, especially in this community. So everything started, interestingly, exactly 10 years ago. So I first sort of learned about foreign clauses and really started to pay attention from this TLDI 2012 paper by Andrei Verbolchenko and his students. And they had this idea that instead of writing model checkers for different systems, you might as well just write model checkers for horn clauses, and then you can use horn clauses to model different model checking algorithms or different proof rules. And this is sort of the first time when I started to pay attention that, oh, there's this interesting format. It kind of solves a lot of the problems that I have if I'm looking for a new format, new kind of transition system. So transition system is functions or things like that. It just fits right in there. And then in the same year, Christoph Hodder and Nikolai Björner had a paper on generalized property-directed reachability. And at this point, IC3, the model checking algorithm from hardware based on SAT, was new. Everybody were looking at how to interpret it from SAT to SMT, how to apply it to software. And this paper, at least for me, really sort of crystallized this point that if that's what you want to work on, if you want to do IC3 for software, then really what you're doing is solving horn clauses, from the first paper. And this is really a nice setting. Moreover, it now just becomes a problem for SMT solvers. And then in SMT workshop, this is made even clearer, where there's a paper that talks exactly about, so what would be a potential extension to SMT-lib, what would be the problems with that extension, what fits, what doesn't, but basically saying that, CHC just fit very naturally in SMT-lib, and they capture this model checking problem. And then in 2014, together with Agnieszka Muravelli, who was a student at Carnegie Mellon, where I was, we created the first version of the tool that became Spacer. And it was very much influenced by all of those ideas. I'll talk in a little bit about sort of what makes it different from GPDR. And this was a big thing for us because it gave us an algorithm that had better performance characteristics than GPDR, but implemented in the same architecture and sort of with an ability to eventually be part of this tree. And then in 2015, we came up with a tool, Seahorn, which sort of the goal was to show that this is not just something that you can do in theory and you could study how to make this problem be a SMT problem. This was, to my knowledge, the first verification tool based on just translation to horn clauses and then making the SMT solver do all the heavy model checking work. And at the same time, be competitive against the state of the art, whatever is happening at software verification competition. And then in 2018, things sort of took yet sort of another big step. Spacer was included in this into the master branch as sort of the default CHC solver. So that made it available immediately to lots of people, that if you just take this and you give it something which is in this fragment, Spacer gets activated and does it. And then we also started the CHC competition that gave us a more restricted format and encouraged other tools to enter the space, or other tools that were actually already available to try and support common format and make it easier for users to then exchange different tools. Okay, so just briefly to show you, so some of the work with using horn clauses for verification. So one of the things that you gain is that you can model different verification conditions. And I don't want you to really look through the slides, through this particular slide, but really just to sort of get an idea that it's not a one-way direction. Just like in general and logic, there are different ways to encode something, and different encodings will have different characteristics. Some encodings are better for some algorithms. Some encodings may be abstractions of other encodings, so some may be more precise. And this opens a space for you of different ways to translating your verification problems into logic. And interestingly, that the horn clauses are really sort of a nice fragment. Almost no matter what you do, if you try hard enough, you'll end up in it. So even if you're not, for example, trying to get horn clauses in the first place, if you're doing something like weakest precondition, you just happen to end in that fragment. And then there's been a big explosion of then sort of going after this idea, and you can show that you can capture all kinds of modular rules. You can talk about parameterized verification, distributed verification, all in this nice framework where you say, oh, the only thing that's changing is potentially the proof rule that I apply. It makes it really nice to compare and understand connections between different, seemingly distinct things. Just again, to make this a little bit more precise, so here's an example of how this works. So here we have a little program in some imperative language. Think about it as C, but cut me some slack. There's no overflow. Everything is integers. There's no pointers in this example. And if you can think how under some semantics this makes no sense, and just pick the semantics under which it makes sense. So that's our program. And then this is what the horn clauses for it would look like. Now, when I write them, everything is implicitly universally quantified. So if you see a variable that's not quantified there, the for all, that's just been cut off. It's on the other side of the slide. And we get these three clauses, as we saw before. Not actually by chance that we get exactly three clauses. So we have the first one, which is the initial condition, the second one, which is what happens in each iteration of a loop, and the last one that says, oh, check for some condition during a loop iteration, and if it happens, jump to false. And we can take all of this. We can actually write it down in SMT-lib. And if we write it down in SMT-lib, like it is the normal SMT-lib. Again, some people were asking me today, so, is it different semantics? Is it somehow not quite normal SMT-lib? Can I just take this input and give it to an SMT solver that never heard of foreign clauses? What's going to happen? And yes, you can. And good things may happen. So you should try. Because this is just a formula with universal quantifiers. Really, the difference is what are we trying to do when we solve it? In constrained foreign clauses, what we're trying to do is to construct the model for the predicates. And we're looking for a model that we can express using, for example, arithmetic. An SMT solver will usually try to solve this problem by quantifier instantiation. And this will be kind of like looking for a counterexample. And then if there is a counterexample, that actually may be an effective way to do it. And if there is no counterexample, it will never come up with a model that it cannot express if it's not trying to express models using, say, a language like arithmetic. But if we give this to this three, it knows what to do. In fact, it knows what to do because we cheat a little bit and we tell it, use set logic horn. Don't use other things, but you can actually try with all of those examples, remove set logic horn and see what happens. Here it comes back with this answer. It looks cryptic, but this is just because SMT solver is cryptic sort of by design. But if we uncryptic it, it gets us something like this, which looks somehow less cryptic, also similar symbols. And if you look at my program, and if I had more time, and if I was teaching this in class, would see that, yeah, this is actually an inductive invariant that you would want to find in this case to prove this problem. I just wanted to show an example what happens in case of functions. So I'm going to sort of go back and forth and touch on this notion of nonlinear foreign clauses, what we do with them and why, but most examples will be simple loops. But again, everything, so here, the examples are simple loops, but under the hood, it supports nested loops and function calls. It's all about the same. So here we have a little piece of code with a function. So in this case, the function itself is not recursive. I'll just factor out increment. So think about it as some kind of modular proof, where even so you could inline the function you don't want to. And you would like to find what is the summary of the function that's good enough to prove the assertion. Again, if we want to write it as foreign clauses, what happens here is now that we have two unknowns. One is inf, which is the reachable state of sort of the main program. And one is inc, which is a summary or specification of the increment function. It has two arguments, the input and output, and it has to relate it. And then we have our clauses, which, one is defines the inc, another defines the initial state, the step, and the property. Right? After you've done this for a while, or if you ever programmed in Prolog, you'll find this very natural, like that's just the way to describe things. And again, we can type it into SMT-lib, not any different than any other SMT-lib. We fit it into these three, and it gives us an answer. And again, if we try and actually read it and simplify it and make it less cryptic, we find out that what we get here, the inductive invariant for the loop is that the counter is never greater or equal than 5. And we get an interesting summary. So we didn't actually need to know that the increment always adds 1. It's enough that the increment, what does it do? That it's always x1 is always less than or equal than by 1. So that's how it works. So what would be applications of this? And from the beginning, we sort of looked at this as two different applications. On one hand, just like anything in logic, this is a great place to try things out. So if you want to prototype a new technique and you don't really care about scalability, but you care about whether it's going to work, you want to make it work on something small, this is great. You fire this off, you type your constraints, you see if it works. Sometimes you'll get surprised and you'll see it actually works for everything that you want. And even if you type more and more, it still works. And then you shift to this bottom part where you say, well, maybe I can actually build verification tools that are really based on just translation to an SMT solver and letting it do all of the work. It doesn't always work completely. After you've been at the bottom step for a while, you kind of want to start going back to the solver and saying, I want to give you my specific heuristics. And maybe I want to build my own solver targeted for my problem. And you see the same in SAT and SMT. So in SMT, we've heard just now that whenever you have a new problem, you often develop a new theory, which is somehow you add more domain knowledge into the solving. We're not there yet with CHCs. So for now, it's either you reduce to CHCs and it works. And if it doesn't work, well, you fork your favorite CHC solver and you start hacking it. Initially, this is how the picture looked like. So we started with spacer. It really was started just as an attempt to study IC3 and understand how this would look like in SMT context. We just generated benchmark to it from various sources just to see what happens. And then somebody suggested that we should retarget a verification tool that I had to generate horn clauses. I said, sure, it'll take about a week. And about a year later, C-horn appeared. And so we've had this. And this really simulated a lot of other, both of other collaborators of mine, but also other people that I don't even work with, to sort of go around and try and build tools like this. So a whole bunch of tools appeared very quickly. Some of them adopted our name. So adding horn to everything, you get a new tool. And this has been for a while. Of course, tools appear and disappear, people move. So this is a fairly old slide. This is how it looks like in 2022. Again, this is not all the tools that use spacer, just the one that I sort of happen to know. People usually don't tell me that they use it. What I wanted to point out here, I guess that there's a large collection of tools and more than just program verification. So people have used it for type infer. This is sol type. There's at least two talks at CAV that use it. One, Sol CMC kind of uses it in a way that it was intended. It goes from some programming language into verification. But another one I was quite surprised with, which is data trees, that was talked about yesterday, that uses it to do emptiness of tree automata. There's also work in trying to use it, say, even for synthesis. There's a tool Messi from Loris De Antonis group that uses it in spacer in a completely unexpected way. Like I still can't wrap my head around how it works for them, but seems like it is. So I wanted to give just a quick overview of the current state of the solvers right now. So we have multiple mature solvers. Spacer is one, it's inside the three. There's Eldarica, which is maybe one of the older one. Freckly or Golem, and there are others. If you want to know about solvers, you can go into the CHC competition and see what's happening in there. In 22, so it's been annual since 2018, we have 7 tracks, 5 + 1 solvers. The +1 is spacer because it's often doesn't compete because one of us is organizing, so it's on a side that doesn't get any medals. And we have a growing collection of benchmarks, which I encourage anybody who's working in this area to keep contributing them to us. We have a scheme where we use GitHub and just copy repositories for that. So what I wanted to do for a more technical part of the talk is I wanted to go and talk a little bit about how the solving in spacer actually works. I'm not going to go, obviously, through all the details. I really want to highlight sort of some of the key aspects that made this work. And I'll talk about some of our new work that tries to improve on them. So first, we need to know a little bit about complexity. The first thing that we need to know is that almost anything here is undecidable, right? So we have horn clauses with arithmetic, we have counter automata, that's undecidable. That's the place we want to be. At the same time, there are things here that are decidable, and we want to not lose track of that because we don't want to say, oh, everything is just too hard, we can't solve anything, let's just use heuristics and nothing else. So every time we make anything finite state, so whenever we say our constraints are propositional logic, things become decidable. So that's that. There's also some interesting classes where things are still a little bit open in terms of, for example, whether our procedures happen to be decision procedures for them. So if you take something like timed automaton, that will correspond to constrained horn clauses over difference arithmetic. There's a question, this is a decidable fragment, but there's a question whether the things that we do are actually decision procedures for them. Now, of course, there's lots of ways to solve this problem. This is really just a model checking problem in disguised of SMT. And anything that was ever done for model checking is applicable here. I'm going to talk about this last part, which is basing off the IC3 model checking algorithm. So I've mentioned this already quite a number of times, but I haven't had a slide about spacer. So this is what it is. It's inside this tree. The easiest way to use it is you just get this tree, set logic horn, and you start using it. There's a private fork that I have if you want some of the latest and greatest things. It supports a whole bunch of theories. Actually, it supports almost everything you want to some level. And so it may work for you. Certain things we work on and we stand behind. And so if it doesn't work, we'll say, oh, we need to fix it. Certain things we barely support. And if it doesn't work, we'll just tell you, surprised that it worked for you before. But interesting to know why you're using it. And maybe we can find a way to do it. And then I keep pointing out that we support linear and nonlinear horn clauses because there are many tools that when they just enter into this space, they only do the linear ones. So where you cannot do modular proofs, where you can just do inductive invariant. The way the tool works that for us, there is really no big difference from one to the other. So whenever we think of the problem, we always just think about the problem as it is. And so we don't keep mentioning that we do nonlinear and things like nested loops. It's all sort of works out. But there's lots of other techniques which are more limited. Okay, so how are we going to solve this undecidable problem? And solve is always in quotes. The problem is undecidable, so we're going to use some bit of magic. So you already seen some magic head appearing before. You're going to see a magic head appearing somewhere in the middle of some slide to show you exactly where the magic is. But this is our guide. So we're not going to do it in a completely ad hoc way. We have a way to go. We're going to start with some decision procedure P for some decidable version of our problem. Once we do this, we have to pick one or the other. We have to give up something. So we can either give up that, we can either require that we always terminate with some answer. That's an over approximation. This is what's often done in abstract interpretation. Or we can give up in another way. We'll say we'll maybe never terminate, but we're always going to make progress. Right? And progress here is from perspective of refutational completeness. That means that if something is unsat, we'll eventually discover it. If there is a counterexample, we'll eventually find it. But we may go forever looking for a counterexample if it's very far. And even if there is no counterexample, we may diverge looking for it for a long time. So that's under approximation. Make one of those choices. And then now we build a procedure Q that tries to be like P on decidable fragments, and then tries to do something better on the undecidable. So in case of spacer, P is the IC3 decision procedure, and Q is the spacer procedure that we do. Now, the guiding principles that we follow in spacer is these two things are really critical for us. One is we want to make progress. So we never want to get to a place where there is basically where we lose refutational completeness. So it's really important for us that if there is a counterexample, after some time, the system will find it. We never want to get stuck in some finite part of an exploration of the state space. And the second thing is we want to keep decidability. That is, we really like a procedure that if you take it as is and you apply it on a fragment that is known to be decidable, then it is a decision procedure for that fragment. Now that's difficult and we don't know all the decidable fragments. So usually what we do is we look at it as at least a decision procedure for the finite state case. I mean, if it's not, that's really a big problem for us. And then whenever we study a problem, whenever it's something new, we look for at least some class of problems where we know that they're decidable and that our thing is a decision procedure. Even if that decidable fragment is very restricted and not very interesting and nobody wants to use it, we still want to have it as a guide to say, okay, this is not just an arbitrary ad hoc collection of rules. It is something, something sufficiently interesting to be a decision procedure for something. So I said that we're building on IC3 and IC3 PDR from hardware, really building on these two works, the original work by Aaron Bradley on IC3, and a work by Nikolai and Christoph on extending this to sort of generalized PDR. The basic premise of how to do this is this idea of verifying by incremental generalization. There's going to be a loop like this. We're always going to look for a finite counterexample in some way. Whenever we find this counterexample, if we found it, okay, we're done. If we're not, we're going to extend it somehow to an explanation why there is no counterexample, some kind of proof. And then we're going to take this proof and check whether it happens to be inductive, or we try to make it inductive. And if that works, we're done. If not, we go for more counterexamples. In all of the steps, there's going to be SMT calls. So everything that I do from now on, every time I click and you see something new on the screen, there is an SMT call somewhere behind. This is roughly the architecture that Spacer follows. The central thing to the architecture is this notion of a proof obligation. This is something that we want to prove as reachable or unreachable. In the beginning, this is just the false of the horn clauses. It is just the state that violates the property. And then we generate predecessors of that state, trying to get to the initial fact. If we can, we get a counterexample. If we can't, we block it and we build what we call lemmas, which are explanations of why this particular thing cannot progress. So I'm going to give a little animation of how this works. And for that, again, I'm going to use the 3 clauses. But now I'm also going to tell you that actually the 3 clauses are not just a fluke. In fact, we can show that it doesn't matter how many clauses you have, as long as your system is linear, you can always compress it down to just 3 clauses. Okay? And if you think about it, it's kind of the same problem that if you have a program with an arbitrary loops structure, I can always compile it down to a program with a single outer loop. We don't actually do this compilation in Spacer. We actually like to use the separation so some things like control flow graph gives us. But for understanding, it's easier to just say, oh, anyways, it's just one loop. We don't need to worry about one. So we're going to look at one of the bounded runs. What you're seeing here in blue is a 5 unfolding of the system. What you're seeing in gray is one of those proof obligations. And here we're trying to prove that we're going to get something bad if after 5 steps we get x equals 1 and y equals 0. We keep going backwards. And every time I go backwards, as I said, this is a call to an SMT solver. And then we extract from the model, what is the value of every variable. At some point, we won't be able to go back. If we can always go back, we get to the initial state, we have a counterexample. We're going to get stuck. And basically using the same theory as IC3, we can discover that if you get stuck, then you can explain that in the first 3 steps, you can never get x equals 3, y equals 0. That means you always have x is not 3 or y is not 0. And maybe with a little bit of tricks, you can actually discover that it's always the case that x is less than y, which contradicts this proof obligation. And you're going to learn your lemmas, which is this purple things at the bottom. And then the game continues in the same way. We keep going back, we're asking for a different proof obligation. Now different predecessor, but now the one that satisfies all of the previous lemmas. And it's going to go back and back and back. And for the purpose of this example, I want to get to a state where we blocked all possible derivations. There is no derivation of false. We now need to generalize. And what we do is what we have here is this partial proof. It's a bounded proof. It's what you need to know for exactly these 5 steps. So we start generalizing it. Again, using an SMT solver. There's a query at the bottom that we do. But essentially, all we do is we find some inductive subset out of those building blocks. And if we happen to do it, which is visually, you'll see it here, that we have 2 frames that have exactly the same set of lemmas, then we've converged and we found an inductive model. So this is roughly how IC3 works. As I said, in the generalized PDR, they show that like this really maps nicely to constraint horn clauses. So just, that's it, basically problem solved. Until you start looking deeper, and there's these 2 problems that you see. So this is just a description of the IC3 algorithm as a collection of rules. There's 2 important rules in here. Predecessor, how do you compute a new proof obligation? And new lemma, how do you generate new facts? So we're going to start with new lemma. And this is really important one because we found some local conflict and we want to get an explanation. An explanation has to be much more general than the local conflict. Let me skip the slide. since I went ahead. So if we write it down, this is how it looks like. What we need in a new lemma is we need to find phi prime. We have the transition relation or the constraint of the Horn clause. We have the proof obligation. We know that they're separate. We need to find the phi prime to explain this. Okay? And if you look at this, you'll immediately say, oh, I know how to find phi prime. And the solution is, well, phi prime is an interpolant. Well, if phi prime is an interpolant, then I can use interpolation to find it. And this is what we do. And there's a little rabbit jumping up. Okay. I'll talk a bit more towards the end of why the rabbit come out. But interpolation is key because it will come up with new, seemingly impossible explanations that come out of thin air that are really, really useful and eventually get everything to work out. Or it doesn't. Okay. Now, the interesting thing here from perspective of interpolation in Spacer, that the interpolation problem is a lot simpler. The typical interpolation problem also requires that the explanation is only over shared symbols. Here, if we dive deeper, the proof obligation has all of its symbols shared with a transition relation or with a constraint. So we don't need to eliminate symbols. We really need just to get a better explanation. And we went as far as we're starting to call it not interpolation, but really an interpolating unset core. So we want to get a subset of constraints that make it unsatisfiable. But in addition to taking subsets, we're allowing you to create new constraints, which are implied by constraints that you have, making them more general, that make the whole thing unsatisfiable. Now, the second step, this one is a little bit more principled. This is computing a predecessor. So we need to compute this S. So we have our constraint, we have our proof obligation, and we need to compute S that lives inside sort of the pre-image over this constraint. And so clearly, if we could do existential quantifier elimination, that's what we would do. But we don't need to do the full quantifier elimination because we just need to find one of those predecessors. The whole thing works by blocking something that is very specific and then generalizing it using, say, new lemma and potentially blocking many other things. So we don't want to generate, for example, the whole predecessor set if that's expensive, because maybe by blocking just one specific one as an explanation, we're going to generalize and block a whole big set. So we need to be able to sort of solve this problem quickly. And one thing that we notice is that every time we need to solve it, we already called an SMT solver and we have a model that proves that there exists at least one predecessor. And so we started looking into how can we do the projection, but guided by a model. There's a formal definition in here, but let me do a few pictures. So here, if I have this formula phi, I want to get rid of x. Well, conceptually, I can think about this exist x of phi as just some space of models, right? So this round thing is just all models of that formula. And because this formula can be written down, at least in the theories that we work, well, then we can write this formula in DNF like this. But so far, I'm not going to write it in DNF. I'm just know that it can be written in DNF. So that means the space of models can be partitioned like that based on how the DNF laid out. And I know that I already have a model. So I have a model M that proves that I have a predecessor. So it lives inside one of those disjuncts in the DNF. And my goal is now just to find, say, psi1 in this case. Right? And you immediately can see here that whenever we're going to do this, it's going to be a finite process. So I compute one predecessor, I get one model. I'm going to block something, which is going to be all of psi1, maybe more. In the worst case, I'm just going to block psi1. And then whenever I get a new model, well, there's the final finite representation of this in DNF. So we have finitely many predecessors that we can possibly compute, which means we're never going to get stuck computing predecessors. Even so, there's possibly infinitely many predecessors if, for example, we are in arithmetic. Now, this is really cool. So I want to go a little bit deeper into it and just really show you how this is implemented. So we start with something like Fourier-Motzkin. So this is a procedure for quantifier elimination for arithmetic. Something is written here, but let's just do a more precise, simpler example. So any formula we can rewrite as a bunch of lower bounds. So here we have S0 less than X is a lower bound of X and lower bound S1 is a lower bound and so on. and a bunch of upper bounds. If we want to eliminate X, well, what we have to preserve is whatever bounds we can derive between the lower and upper bounds. So basically, for every pair of bounds, we have to create a constraint, right? We have a quadratic blob, we have more and more variables, it keeps blowing up, keeps blowing up. That's why quantifier elimination is expensive. But is it always the case? What if we have some kind of nice assumption, such that under this nice assumption, we can actually write an exact quantifier elimination in a very compact form? Now, how do you get this assumption? I don't know. You read other papers, look around, think hard. But in this case, in arithmetic, here's a nice set of assumptions. What if I take all of my upper bounds, and in any particular model, there's always going to be the smallest upper bound. So say I make an assumption that T0 is the smallest upper bound. Then now all I have to do is to say, well, it's the smallest upper bound. That's n constraint. And then every S is lower than that particular upper bound. Okay. And again, easier if we just look at an example. So same thing as before, but now I have an assumption. I pick T0 to be the lower bound. And then I have the quantifier elimination under that assumption, where all I have to do is just say, well, if T0 is the smallest, then S0 has to be less than T0, and S1 has to be less than T0, and S2 has to be less than T0. That's it. Now, this formula is now linear in the original. The question is, well, how do I know which assumption to pick? Well, I have finitely many assumptions, the different orders. Which one do I pick? Well, it's easy. I have a model. Right, so I'd like to find an under approximation of quantifier elimination that is actually contains the model that I have. So I pick an assumption based on the model. Right, so I have my space of assumptions. I evaluate all of the assumptions in the model. I pick the one that's true. Now I break ties in some deterministic way, and then I generate my predecessor. Right? And this is really this has been really powerful because on one hand, you get to be guided by the model and you get the speed up from that. On the other hand, we're not taking anything from the model, right? As soon as we take, for example, a value that the model has, then everything goes haywire because there's infinitely many possible values. So we have some guide, but not an actual value. And then you can wrap it into a nice simple procedure. So there's a recursive procedure that goes and computes model-based projection based on the model. You do it as much as necessary. And of course, whatever you do with upper bounds, you can do with lower bounds. So now you can optimize and pick the one that's better for your form. So this gives us the predecessor rule. So basically, it's instead of quantifier elimination or instead of just picking one model, we use a model-based projection. So this is spacer, but for linear horn clauses. Once we get to nonlinear horn clauses, well, there's one extra problem. We now have to deal with the middle clause in here, where we have two predecessors to create. And the question becomes, well, how do we break a single predecessor from the constraint into the two directions? Right? Because we may get something, so here, maybe this is not that obvious, but here we have, one predecessor talks about X, one talks about Y, but when we do a predecessor of a constraint, we talk about some term that has both X and Y in it. How do we get rid of one but not the other? How do we do it in a good way? And again, quantifier elimination, model-based projection. We can project onto the X space. We can project into the white space. So as soon as we have projection, all those problems become easily solvable. And so now finally, what's left is how do we explore in case the system is nonlinear? System is nonlinear, it grows into a tree, right? Same as the data trees that we saw. And so here again, we're going to use model-based projection to create predecessors, but also model-based projection to create under-approximating summaries so that we don't need to explore the whole tree. So the overall exploration looks like this. You call an SMT solver, it says there is a predecessor, and you have this model that sort of has the values for the two predicates on the side. You use model-based projection to push everything towards one, say towards the X variable. You have a new proof obligation to solve on the left. You again call an SMT solver. You get something like that again. You do projection. So in this case, we're going always left. Eventually, you're going to hit the initial fact. And if all of this part happens to be satisfiable, we don't yet have a counterexample. Essentially, maybe what happens is we're looking at, say, how the main function works, assuming that the increment function, we don't have any spec for it, it's just non-deterministic. So just because we found a counterexample under this assumption, we still need to check the other function. So in this case, we start going up. We start computing, well, we know something is reachable, something is derivable, but we want to derive a whole bunch of facts, a bigger under approximation. And again, we can do it using the same sort of symbolic quantifier elimination. And again, we always have models, so we just follow those models up. So we go up one level. Now we can compute the proof obligation for the other side because we have an under approximation. So what can the, say, P of X do? And then again, it goes down, up, and so on, until eventually we get to the top, which is our bed state. And if we manage to do it, now we have a complete counterexample. Right, so one thing you'll notice here, which is very different from IC3, is that we don't just always go back and stop, we always go forward. Right? And this idea is actually interesting in case of IC3 as well. So some of the things that we've done over the years is taken ideas that came from Spacer, ported them to IC3, and found things like that computing reachable states through some form of under approximation is also interesting in that case. But this idea that we can go both back and forward is actually very useful because now we can do arbitrary abstractions and we don't have to worry because when we go back up, we essentially validate our abstraction. So this is so the spacer overall as a set of rules. Again, I don't really want you to read the slide. It's really if you want to look at the slides later. But I want to jump into some of the new things, which is what I call the curse of interpolation. So I think the main reason why Spacer worked and it was successful when we started is really these two concepts. One is we can reliably explore the space of predecessors. We're never going to get stuck in a problem that, for example, you can solve by BMC. And the reason why we'll actually terminate is always interpolation. It gives us the useful building blocks. So it's really, really important. But the problem is that interpolation is very unpredictable. Right? We're doing generalization very locally. We're basically asking an SMT solver, why did you think this happened? And it gives us a reason. And sometimes this reason is something like nice as A equals B. Sometimes it's not nice, like A plus B less than 4. Sometimes for some problems, A plus B less than 4 is actually the nice one, and A equal B is not the nice one. And there's many, many choices, and an SMT solver doesn't even know which one to do. We spent quite a lot of time working on this problem sort of in that particular space. Can we do better interpolants? Can we somehow define what does it mean to be better interpolant? Is it, for example, an interpolant that has no constants? Or is it an interpolant that has a certain shape? And none of those things really are satisfactory. You can build them in your tool, and then you can improve on certain benchmarks, but you'll always know, what numbers to put where so that this whole thing goes back and doesn't work. And so this led us into this line of work to try and look at more of a global view of what is happening in addition to the local view, and try and see if we can make decisions based on this global view. So this is a nice cartoon summarizing the paper by Jeff. It's actually very accurate. So if you read it and then read the paper, you'll see actually everything that you need to know is in here. I'm only going to talk about myopic generalization today. So let's see. So it starts like this. You get this example. I get them a couple of times a year. It's always the same example, slightly modified. The trick here is that we have a whole bunch of variables that are incremented in tandem. They are actually related because they somehow start in a related state, but nowhere from the syntax here, it's apparent that they're related. Okay. And sometimes your interpolants will be nice and they'll give you nice relations. And sometimes they'll be not nice and they won't give you nice relations. So if we look what happens with spacer when you solve it, so we have this little visualizer. So this represents the exploration I was showing before. And all I want you to look at is at the bottom, the different facts that we learned. So as you see here, we're looking at bigger and bigger systems, and at the bottom, you see the fact that we learned. You spend 3 seconds looking at it, and you'll tell me immediately, this thing doesn't converge. It's never going to converge. Don't let it run longer. It's just stupid. It should somehow figure out that all of this can be expressed in one same way. And so this is what motivated us to look at this. And so this is a form of data-driven generalization, where we want to look at the data that's produced in a proof, somehow mine and cluster it, and then try and find ways to reduce, have the same information, but with less symbols. So this is what we call global guidance. There's, so maybe I'm not gonna explain all of the animation, but the point is that in addition to what Spacer is doing, now there's cool glasses and a control center that looks at what's happening and controls things over there. We have these 3 things, subsume, concretize, conjecture. I'm only going to talk about subsume, this combination things. Sometimes combining many things doesn't work, and so there's other things to maybe break things apart or maybe abstract things away. But I'm only going to talk about one. And conceptually, the rule is really simple. It says, imagine that in your space of lemmas, green, you have a whole bunch of lemmas where you can find one blue thing that subsumes all of them and is also a lemma. Then go for that one. The question is, how do you find your set L, and how do you find the blue thing to go after? So visually, it kind of looks like this. So we have a whole bunch of green things that we're learning. So this is lemmas, that the things that we know. And somehow, if you look at this, and depending on how your intuition is by looking at formulas and pictures, you'll sort of see immediately this corresponds to the formulas I was showing, the kind of boxy, and the kind of thing that you want is a relation, which is kind of a line like that. And the way this works actually, so if we look at the formulas, this is the green space. This is the thing that we're learning. And what we need to do is, first of all, figure out that these things are related. And what we do in the current case is quite simple. We really do what you do with your eyes. We isolate all the numbers, and we see whether the formulas happen to be the same, except for the numbers. If so, we put them together and we say we need to do something. And the thing that we do is essentially convex closure. It's easier to see it if we look at what we are blocking. So here you're seeing what we learned. And what we learned is the dual of what we're blocking, what we made impossible. So these were all of the proof obligations that were blocked. There's a disjunction of them. So in this case, there's 3 orange proof obligations that were blocked. And what we're interested in is whether we can represent them by a single conjunction of inequalities that is bigger than that space. And that's convex closure. So you can compute the convex closure of those inequalities. That gives you this magical term, this one here. This is exactly what interpolation does. It also gives you those magical terms. But here it's a little bit more principled. We're forcing to get that term. We're computing that term. We're not getting it from the proof just because an SMT solver decided to do it. And then once we have it, we can do other sort of normal IC3 generalization, like dropping literals. And in this case, we'll all of a sudden get something that looks kind of nice. And of course, this is all just a conjecture. So we take it as a new proof obligation, add it back into an engine, see if we can learn it. And if eventually we learn it and it ends up in our lemma space, then maybe that will be a good building block for something inductive. Right? And so we end up learning something like that. Okay, so so in summary, the basic idea here is that you need this notion of clustering and this notion of merging. Both of those things we have done for some things, but this is still quite open. So we looked, for example, in the beginning at maybe using some AI clustering techniques, and none of them really worked for us. So we ended up with something very simple, anti-unification. You just see if 2 formulas are exactly the same. Maybe you do little semantic manipulation, but just barely. And then it's important that once you have a cluster, you have a way to act on it. So you have cluster where, for example, if you take a convex closure, then you're going to get a good candidate, as opposed to, for example, a cluster where if you take a convex closure, you get the whole space, and then this is not that interesting, and maybe there's some other action you need to do. For arithmetic, as I said, clustering is anti-unification, merging is convex closure. Interestingly, we actually implement convex closure by model-based projection, there's a way to do convex closure using syntactic means that requires quantifier elimination, which we can then substitute by model-based projection. And then, of course, it's integrated in Spacer as a strategy. So it sort of lives there on the side, creates the lemmas, and you need to, of course, as soon as you put something like that, put all kinds of hoops to make sure that it doesn't overwhelm the solver, that you don't making too many wild conjectures. Okay, so I'm mostly not going to show you numbers, but I want to show you numbers here. And maybe I should actually talk about this part a bit. So usually, whenever we do something new in Spacer, we clean it up and we put it in this remaster. And this particular thing has been on the site for quite a while. And I've been promising to finish and clean it up. And it's finally at least a publicly available pull request. It's always public in our forks. But if you want to try it out, go for the pull request. And hopefully, in a few weeks, I'll eventually get it merged in a master and it will just be there. Okay, so I'm not really want to show you numbers because you really can't understand them unless you really understand the benchmarks and like so can understand what the meaning of this. But there are a couple of interesting things here. So one thing here is we tried looking at Spacer versus GSpacer with interpolation disabled. Okay? And that's an interesting comparison to see sort of what is the effect of interpolation. For Spacer, it's huge. If you look at how many more instances Spacer loses whenever you remove interpolation, that's a significant amount. With GSpacer, interpolation doesn't play all that significant role at all. So that's sort of an indirectly showing that really a lot of the work that interpolation is doing is convex closure, is some kind of resolution of arithmetic literals, and we can do it in a different way. Now, the second thing that I want to show you is what sort of under the hood motivated us. This was our main motivation. There was a paper in PLDI and said, we can do constrained horn clause solving using machine learning tools, only machine learning, no SMT, data-driven, and it works much better than Spacer. And so we read the paper, and all that we understood from it is that there is a lot of convex closure happening in machine learning. And we don't do any, and that's probably where we're losing. And so that's motivated us to look into this direction. And so we had to do a comparison with them. Now, of course, this data-driven thing, it's not surprising that it's tuned for particular kind of problems. So when we tried it on the benchmarks from the competition, and the competition happened after that paper, so they couldn't do that, this tool doesn't perform in any way comparable to Spacer on a wide variety of benchmarks. So instead of doing that, we went to their benchmarks, the one that they were using. And in fact, we could see, yeah, Spacer itself without the new things does pretty poorly. So I think we do 2016 safe instead of 270. But as soon as we add this global guidance, the picture changes. So Spacer remains as competitive as it was on a wide variety of benchmarks, and also in this particular ones that were sort of crafted to exploit these problems with interpolation, it now behaves quite well. So I think I'm going way over time that I wanted to do. So I'm gonna just skip over a little bit and then slow down towards the end. So one thing that I thought would be fun to tell you, but I'm gonna skip, is how all of this then helps with bit vectors. Because bit vectors have these two big problems. Quantifier elimination is either easy, but not very general, so you can just plug values in, or really hard. And there's no good interpolation that can generalize. And so we show that with model-based projection, we can tune quantifier elimination to the easy cases. So for example, we can say, if in a current model, the variable is small enough and there is no overflow, then do quantifier elimination like you would do in arithmetic. And in other cases, plug in. And with global guidance, we can again get away from needing interpolants, where we could say, do something with more or less concrete values, and then we're going to compute convex closure over arithmetic, and that's going to be a conjecture anyways. So we're going to put it back into the solver and then see whether that happens to work on it. So this is the slides that I'm going to skip through. Just going to point out, so the model-based projection, so there's this step of rewriting, because we want to put the variable that we're eliminating on the left-hand side, isolate. And again, we can do this isolation using rewrite rules, which are specific with a whole bunch of site conditions, and we can mine the site conditions from the model. And if no rule applies, then we can just replace the variable, the value by the variable by its value in the model. And then the model-based resolving is similar to the arithmetic, except it's all over integers and you need to worry about overflow. So the rules are tedious, but more or less the same thing. So here's an example of a rewrite rule. This is an inference rule top down as a rewrite that goes bottom up. So we're isolating T of X. And here's just a snapshot of how resolution happens for arithmetic. If you squint, you'll see here that we also pick the largest and the smallest and only resolve that one. And there's lots of side conditions to make sure that we can trust, even so that there's a bit vectors, nothing overflows with all of the multiplications that we need to do. And then, of course, this only handles arithmetic. So for anything that's not arithmetic, we just have a hack where we factor the formula into the arithmetic part and everything else that it may do. And whenever things don't work, we just project, replace the values by the values from the model. Bit vectors are finite, we still get our decidability, but obviously this would not perform well if there's little arithmetic and a lot of, say, bit shifting in your bit vectors. Okay. So towards the end, what I thought that since I have the space and I have your attention, that I can tell you a little bit more about the space of CHC solvers so that you don't come from here thinking that, oh, constrained Horn clauses are great and I should use spacer and there's no other tools. This is a space that is actively being developed. There's quite a few other tools that you should be aware of and potentially try as well. First of all, there is a CHC competition. The latest edition was in 2022. We managed to keep running it all the way through the pandemic. As I said, there's a whole bunch of benchmarks in there. There is a simplified format. There's all kinds of tools to put things into that simplified format. So if you either want to donate benchmarks or you want to try some idea on this kind of space, the easiest way is to go to the competition benchmark. Just support each format, don't build a full complete tool. So in terms of solvers, I picked a few. So one that I really want to talk about is Eldarica. It says here that it started in 2011, I think. So I asked the authors of the tools to prepare slides for me. This is probably the oldest tool for constrained Horn clauses. As far as I understand, it's really based on sort of the idea of taking classical model checking approaches like predicate abstraction and forward computation and extending them to apply to Horn clauses. So as far as I know, it doesn't, it's not based on IC3-like ideas, but it does have interpolation and also different ways to control it. Some of the fun parts about it is that it integrates with this accelerator package. So it actually tries to find closed form solutions for small loops, which make it much more effective than spacer in some of the small instances. And also, I think we had a talk about the solidity model checker for Horn clauses. Even so, it's using both spacer and Eldarica, and all examples that Leo was showing. Eldarica was the one that he wanted to show. The second tool that I want to show off is Horn. So this takes a very different approach. It's really a model finder for Horn clauses. It says, well, if you can check that solution is valid, then maybe I can just come up with a bunch of solutions, plug them in, see if they work, and if they don't, I can tweak them a bit and get them to work better. And that sort of started as a simple framework just by trying to look at a solution influenced by some grammar. And Grigory Fedyakovich keeps building on it and gets more and more complicated and more advanced. The key difference between it and spacer is that it's really a goal to just see if we can find a model. It doesn't preserve decidability, it doesn't necessarily make progress, it may not be able to find a counterexample, but it may be able to pick a solution out of thin air. And there's a bunch of papers. And then this is from the group of Natasha Shurigina. This is, I think, the newest entry in the blog called Golem. And it goes after taking all of the ideas that we write about and actually implementing them themselves. And that's really exciting because it's never clear. So if you implement something and then you publish a paper, what you put in a paper is some abstraction of what you implemented. And you always doubt, at least I always doubt, whether, the hack that I put in order to get some example to work, maybe that's the key part. And so having somebody to re-implement the algorithm from the paper and actually see similar performance results that we do, that gives me a validation that really the algorithmic part that made it to the paper is the important part. So they said it started fairly recently. It keeps growing, it's already winning medals at the competition, and it has the sort of usual architecture. But the key thing that I want to point to here, when they say spacer, they mean spacer, the algorithm that they've implemented, as opposed to be just feeding it back to spacer implementation in this. Okay, and so the very last thing that I want to conclude with is to look at so what is in the future, what is missing. And there's, of course, lots of obvious things, and we saw that in the talk about SMT solvers. There's always need for more theories, there's always need for scalability, there's always need to make things better and faster and shinier. And so I wanted to look at another aspect, not that that's not important, and that's the aspect of supporting users of constrained of CHC solvers. And here, the word users is very confusing because there are users all over the place. So if I look here, well, there are some users which are people who use the solver itself. They understand quite a lot of details of how the solver works, and they want to somehow understand why it doesn't work on a certain instance. This could be, for example, me. I know how the solver works, but I need more support whenever it doesn't. Or somebody who's closely related to something like this. There are other users, which are users that work in this space where they don't really want to get into the solver itself. But they do want to produce horn clause encoding to it, and they may want to influence the solver in some way. They perhaps would benefit from some API that would expose some part of a solver to them, but without making it too complicated. Right? I've seen this kind of things in SAT solvers and SMT solvers, where instead of saying, oh, just write your own SMT solver, you can inject pieces of your code to maybe affect some kind of decisions. We've done, for example, a little bit of this by trying to add a machine learning guidance to Spacer, but having something that is more generic, not specified to a particular guidance that I have in mind, would be a very interesting direction to go. And of course, there's users who create this VCGen tools. So the promise of horn clauses is that it's very easy to go from an idea of a proof rule and a program to horn clauses. But this is actually really, really hard, right? So we have C-horn. It implements a particular set of proof rules. And if I come up with a new set of proof rules, for example, I'll say, for this class, I want to use a class invariant. And I want to be modular according to class invariant. It's really hard for me to make this happen because it basically requires me rewriting C-horn from scratch with that in mind. And so having some kind of different input, other than saying, I have a program and the proof rule is inside the VCGen. Something that's more like synthesis, where I can say, ooh, I'm missing some of this information that I want, but not general purpose synthesis, because that's much more expensive, is maybe an interesting way to go. And so I wanted to just show one thing along this line. So actually not the last thing, but the first thing, and that's the spacer visualizer. So this is one of the things that we made for ourselves to understand, how spacer works from the inside. We've never managed to really make it public. It is publicly available just to make it usable to other people. It started by Matteo, and it really was a side project. We were working on parallelizing spacer, and he wanted to understand better, so what is actually happening. So he through this web page, he basically made spacers do some JSON, and then it goes into this web page, and you see the exploration. You can click on nodes, and you could see what is the different lemmas are. And this was really instrumental. The previous work that I was showing, like we just didn't see that pattern until we saw it in the visualizer. And then after we've done this, Bernard Gliss was visiting me, and he saw that visualizer, and he said, oh, this would be really cool for Vampire. And he made one for Vampire. Then we saw what he did, and we said, oh, like this is so much fancier. There's web servers, and it's all interactive. Like we want to do this thing, but for spacer. So we took all of his shell, removed all of the Vampire stuff, put the spacer stuff in, and now we have this thing that we called Hubble Spacer Telescope, HST, that lets us look into spacer It shows us what is being explored, what is the different lemmas, whether the same thing was blocked by the same thing multiple times. And it's extremely helpful. I know my students really like using it to understand what's happening. It's been really hard to make it to a point where we can give it to, say, people who use Spacer and say, oh, if it takes too long for you, just look here and then give us a summary of what you found. Still a lot of work to do. So having tools like this at a Spacer level and SMT level that let us understand better what's happening and somehow helps the user communicate, I think that would be a very interesting thing. We've done actually quite a lot of work on this, but we don't really know what to do with it other than implement it. Like we don't know how to publish it or what to do other than, we build, we try. All that we can argue that it helps us. And I don't know if I even want to convince anybody, any community, that this is helpful in general. So it's not clear how to really make progress in it. And so I want to conclude with what I call art, science, and magic of constrained Horn tortoise. There's a big part of it that's an art, which is encoding things in logic. That's always an art. You want to use an SMT solver. There was a lot of great things said about them, but to me, they never work. You start something, you have an idea of how you're going to encode it, you encode it, and it's probably going to be terrible. And you have to put a lot of effort to figure out how to do the encoding properly. This is a big art. The same as with CHCs. If you say after this talk, oh, great, I now have an arbitrary verification platform. All I have to do is just figure out how can I convert my stuff to CHCs. It probably won't work. Also, I've heard from some people that it does work for them, so it might. But at least for me, it never does. And you have to put a lot of thought of how you're encoding and why you think it will work. There's science, which is all the stuff about trying to show that what you're doing is a decision procedure, that you have refutational completeness, that you are making progress. And then there's magic. Magic is actually making it work on useful problems, right? At the end of the day, this undecidable problem, no matter what you do, it's not going to work. And it's very magical whenever it does. And that's it.
Thank you, Arie. This was a great talk. And then more questions.
Hi, nice to hear. Thanks. Because there's so many problems here that are familiar, right? And one of them is, this idea of generalization. We can do it in certain theories. So, sometimes I look on this stuff that also called beautiful interpretants. It was targeted to the problem that we were showing. They could find these invariants that were essentially compact balls of sequences of regions and so on. But the trouble with that was it only worked for arithmetic. And it only worked for arithmetic, and we didn't have a way of generalizing it to other theories. And so I'm wondering what you think about that. How do we get beyond, for example, linear arithmetic to be able to generalize well in other theories and talk about maybe rates, exactly beta that.
So like with linear arithmetic, you have convexity, and it just kind of jumps at you, and that's what makes it work. And with other things, it's hard even with bit vectors, right? So, for example, we do bit vectors by pretending that they're everything. And so now we go back to convexity. You can do certain things with arrays, so you could try and use tiny things like this. So you can, for example, guide it towards array property requirements. And again, that's also convexity and arithmetic. You just mining stuff out of arrays. We've done a little things with data types, but the data types need to create their own recursive function. So far we assume that they do them, so there's less generalization to do. But yeah, that's good. So I think what sort of the exciting part for me here is to realize that we should look at global things too. Right, so the very is that, so how do you cluster things? And if you cluster things for certain reasons, then now you may have a generalization to go with it.
I have a very technical question. In your model-based projection, when you get a DNF, are you getting the picture that it should look like you are getting a distant DNF?
No.
Okay.
Let's see. So some pictures are conceptual. And so let me. Ah. So this is exactly what we. So we're getting this, and I will claim this is one distance from a DNF decomposition of the row. So I'm only using existence of a DNF to prove that this is finite, that this decomposition is finite. That if I keep making this assumption and then I get this distance and I say, is there another assumption that's possible? Because I have a finite DNF, that's going to be finite. Okay? So you're referring to this slide, right? Where I'm saying it is equal to the DNF. I just want to get psi 1 without paying the cost of computing the DNF.
Thanks.
Any questions?
Thank you for the nice talk. So you have this open problem with timed automata. Have you considered that, for instance, another problem which is more amenable to this, which is spectral coverability? So maybe in that case, you have a complete decision proceeding.
I haven't. It's interesting. So what, like, the actual question is, so we have this algorithm implemented spacing, right? And is this algorithm a decision procedure for that input? And if it isn't, why not? And, you know, maybe we're missing something that can be added so that it is.
I suspect you have it because there have been paper about IC3 coverability in spectrum.
Right. There are also papers about the stability of timed automata, and I'm just not sure that we're guaranteed to find that invariant, like that we actually, like, because there's still an infinite space of possibilities to explore, that we in fact explore the finite space of this. Not sure.
I think we have time for one more question.
A very nice talk, thank you. Well, I feel like I'm a user of the tool in several domains. I use your tool to prove correctness of concurrent programs through sequentialization, but now I'm more interested about strings. And the way I see strings, I visit each node multiple times. So like I'm adding information to each node. And therefore, I'm computing a sort of relation for each node that expands. Do you have any advice whether I should do a sort of widget? And I build all this relation completely from bottom up, for example, or it's better in terms of get better performance to make this go. I don't know if that.
So I looked a little bit at your talk, and like this is a very different application for me than I'm usually thinking about. So I don't know. I'd need to, you know, encoding is an art. You try different things. You try and understand how it affects the solver. And
so let me give an example. Suppose that you are analyzing the recursive procedure, and your own process at some extent will build the relations into power. Okay. Now you might guess what the input is, and then compute the output, and then you join everything together and you get to the root. Okay. Now either you can do sort of fixed point where you throw in things, and then when you determine you compute the summary, which one will work better. For example, I did that on the, I don't know if I pronounce it well, is a tool that was built by Arie here.
Mhm.
And but it is based on beliefs. And goal racing would deliver much better performance than doing an inter approach. I was wondering whether there was something like that.
So spacer or IC3 algorithm in general does this kind of abstractions under the hood. And so, yeah, it doesn't, it's harder to guess performance compared to like a forward exploration BDD based tool. So I would try both and then, use the visualizer to see what's happening. And then maybe once you see something, you can actually prove that one encoding is necessarily better than the other.
Thank you very much.
Okay, so let's then Arie again.